In the first part of this video series, we introduced the concept of probability, and we discussed some definition of terms and even computed some examples. In this second part, we are just still considering some theoretical definitions, and we'll still have some examples as we delve deeper into this topic of probability. The first term we're going to talk about is factorial, and we understand that the factorial of a non-negative number integer n is the product of all positive integers less than or equal to n. So what does this mean? It means that if you have a number n, you're going to have a product of it by less by n. So if you have n, factorial is n multiplied by n minus 1 multiplied by n minus 2, and then the sequence continues until you multiply it by 1. But by definition, we have 0 factorial being equal to 1, and this is for the purpose of mathematical convenience. You can have some sources on how we compute this, but this is not within the concept of this video. Some other examples you can just try to compute is 3 factorial, which will be 3 times 2 times 1, and 5 factorial, which will be 5 times 4 times 3 times 2 times 1, which gives you 120. We also had some examples in the first series where we were selecting items, and I felt that it is very important to discuss another important concept known as combination and permutations. And here we were just seeing that sometimes it's more than just selecting, and you may need to adhere to some rules. For example, you are told to select without replacement or repetition, or even you're supposed to follow a certain order. So how do you compute that? And for example, we have a set of 12 bags, and you're asked how many subset of 3 can you make. And this calls for understanding the concept of combination and permutations, because it will help you solve scenarios like this. So just as a snapshot, in permutation, the order of items is important, while in combination, it does not matter. So that's the key difference as you're going to see here. So permutation is the distinct interpretation of a provided number of components carried one by one, or some all at a time. And here we can say if we have a component, we have items A and B, and we are told to select, we can have AB and BA. This means that A, B, and BA are distinct, although they are just the same letters interchanged. They are distinct items. So this means that in permutation, we see that order and sequence is very important. Mathematically, if you are told to compute the total number of elements is represented by n, and then the number of groups that you want, the sets, let's say 3 sets, is represented by the letter r. So therefore, to compute this, we have n factorial divided by n minus r factorial. And here we have an example. The sources, you can read about more on the sources in the video description. And here we were having total number of elements A, B, C. We can make 6 permutation of size 2. That is, from ABC, we can combine and get AB, AC, BA, BC, CA, and CB, as represented with visually here. Next, we have combinations, and here items are selected without paying attention to the order. So while in permutation, we were so keen about the order, here we do not pay attention to the order. And if we have 2 components A and B, there's only one way of selecting these things. So AB and BA is the same thing here, because we are not paying attention to order. We are paying attention to the items itself. So if we have 3 items, that's our N, that's A, B, C, and we need 2 groups, that's our R. That means we have all combination of size 2. Then our answers is 3 items. We'll be able to select 3 combination, that is AB, AC, and BC. And mathematically, it can be visually represented as this way, same as to the one for permutation, where the first, the superscript 3 prior to C means the total number of elements, n, and R is represented by the subscript just after C. So mathematically, you compute it by saying n factorial divided by r factorial into bracket n minus r factorial. The good thing about this, most calculators, scientific calculators, have this functionality of computing this, and makes it easier. So visually, just the same example we were going through here, where we were saying A, B, and BA are the same. So from AB we can get ABC, we can get AB, BC, and CA. So the last terms we're going to discuss in this example is, in this part 2, is sampling with and without replacement. And just as a key definition, sampling is the process of selecting items or observation from a larger population or data set for analysis. So when you have a bigger population, and I'm just going to take my pen here, we have a bigger population and we want to select, and then you want to draw some smaller from this population. So this process is known as sampling, and you can do it with or without replacement. This means that after selecting an item, you return it or don't return it. So let's see in detail how do we define it. So when we're saying we're doing with the replacement, we've just mentioned that it is returned to the population before the next row, meaning that the total population size remains constant for every row. And an example is when you are rolling a die multiple times. So each time you roll a die, so you have your die there, and each time you're rolling it, each time you're rolling it, and the choices remains the same. So the multiple, even though you roll it 10 times, each roll is independent of one another. So this is one characteristic of sampling with replacement, that each roll is independent. Same when you draw a card and then you replacement, or when you shuffle it before the next draw, your end still remains the same. So just the key term in conclusion, when under sampling with replacement, end remains constant and the events are independent. Therefore, this means the probability of selecting an item does not depend on previous selections. What about without replacement? So here, when we've drawn it, we do not return that item we've selected to the population. This means the next time we are drawing it, we are having from a population, we'll have it n-1. And this means each item can be selected only once. Each item can be selected only once. And an example is when you draw cards from a deck without replacing them, and also when you are enrolling study participants. You won't enroll a participant into more than one treatment arm. And therefore, another important example is when you are doing draws for sporting events, for example, football, and you are able to assign a team into one group or into one stage. Therefore, that team cannot be assigned to another one. And just in summary, when you are doing sampling without replacement, events are dependent of one another, and n changes after every draw, and the probability of selecting, this means that the probability of selecting a specific item changes based on previous selections. So let's finish up this episode with some examples, and we're just going to see that here we're having 5 balls, 3 blue balls and 2 green balls, and you randomly draw 3 balls from the bag with the replacement. Take note of that. So it's the probability that all balls are red, and then exactly 2 of the 3 balls are red. So you can pause the video to attempt the example, then come back after you've found the solution. So the probability that all 3 are red, we see from here we have 5. The total number of balls is 10. So n equals to 10. So this means that our probability of red is 5 over 10, which gives us 0.5. So what means that we want red in the first, red in the second, and red in the third. So we are going to apply the multiplication rule, and we are going to have 0.5 times 0.5 times 0.5, and the answer is 0.125. So next, we're going to discuss the second part of that example, the probability that exactly 2 of the 3 balls are red. So what we can do, we can have the probability tree, and just try to visualize the selection process. And we can have, in each selection we have RGB, where this is 0.5, this is 0.2, this is 0.3, all of them totaling to 1. Then this is the first draw, so this represents the first draw. Then we also have a second draw, the same selection, RGB, and then the third one also, RGB. So what does it mean in this tree? So this means that this is the first draw, this is the second, and this is the third. And this means after selecting red in the first draw, the second one you can select any three of them, and so forth. And this goes until even the blue, and also even in the green, just dissects out. And since we are sampling with the replacement, this visual diagram n does not change every time we are having a selection. Each item is ready for selection. And therefore, when we want to say two exact balls, what can we have? We can have red, red, green, red, red, blue, red, green, red, and then red, blue, red, then green, red, red, then blue, red, red. So this means exactly two reds. So when computing this, whenever we are focusing on this part, so we have red, red, green, red, red, blue. So this will have us saying the probability of this probability of red, red, green multiplied by the probability of red, red, blue, the probability of red, green, red, the probability of red, blue, red. This, as you see here, we are starting with the red selection. Therefore, since items are deviating from the same initial selection, we want to combine them by multiplying the product. Then we have the second one and the third one. See this one now, we are doing addition here. So what do we do next? We add the elements that we've gotten here. So 0.05 plus 0.075 plus that and that, and gives us 0.375. So allow me to erase the ink on the slide so that you can do another alternative. We can apply the binomial formula. This is a concept that you're going to see in subsequent episodes in this series when we introduce the concepts about the probability distributions. And what the binomial formula of the distribution just tells us the probability of getting k successes. So, and our k successes was the red balls from n independent trials. So we have 3 trials, remember? We are doing 3 selections and we want 2 red. So we are just going to use the probability distribution, the binomial distribution, and this is how you visually represent this. And when you expand this equation, you have 3, 2, then multiply by 0.5, where p is the probability of successful drawing, and then 1 minus p, sometimes represented by q, then raised to n minus k. When you compute this, it just gives you the same answer, and we are going to discuss into detail in further part of this. So there we have it, and we just sought to discuss these 2 examples, and I hope you've understood the concept of how we do sampling with replacement, its computation, and most importantly, combination and permutations. We are looking forward to more and more understanding into this concept of probability, and I hope to see you in the next videos.